So let's say you have a hot cylindrical tank that's located inside a facility and it's maintained at a constant process temperature. The tank is uninsulated along its side walls, while the top and the bottom surface of the tank, they're insulated. The measured outer surface temperature of the tank, so let's say somebody goes and measures the outer surface temperature of the tank. So let's say you have this guy over here that walks to the tank and has a thermal probe and just touches the tank walls, and he sees that the temperature is 50 degrees Celsius. Now, let's make an assumption, and let's assume that the average convection heat transfer coefficient between the tank and the surrounding air is 25 watts per meter squared per Kelvin, and that the ambient air inside the facility is about 20 degrees Celsius. The question here is asking you to determine the heat loss from the tank to the facility air. Let's assume that the tank height is 6 feet and the diameter is 4 feet. This is a very straightforward question, and when you work in industry, you might find a lot of problems that are similar, but nobody's going to come and give you the average heat transfer convection coefficient like I did in this question. It will be something that you need to look up in tables, or you need to see if there are correlations that you can use. And also, this situation is hazardous. I mean, it's dangerous to an extent, because having a hot tank that is exposed to where people could walk at 50 degrees Celsius is generally not a good idea. You probably want to have insulation. But this is just an example so that we can demonstrate our understanding with using the equations to see if we can calculate what the heat loss is. And then we're going to look at later on how we can calculate how much insulation we need and all of that. But we need to start with simpler exercises and work our way up to more difficult questions. So you can pause this video and try solving this problem statement yourself, and then we're going to solve it together. Okay, so let's look at the solution together. So we know that this is a convection problem, and therefore if we need to determine the heat loss from the tank to the facility air, then we're going to have to use the heat flux relationship for Newton's law of cooling. And Newton's law of cooling, as we said, says that the heat transfer flux is equal to the average convection coefficient multiplied by the difference in temperature from the surface to the air. And we know that it's given to us in the problem statement that the average convection coefficient is 25 watts per meter squared per Kelvin. And we multiply that with the surface temperature of 50 degrees Celsius, so that's 323 Kelvin, minus the temperature of the air, which is 20 degrees Celsius, so that's 293 kelvins. And if you do the math, that ends up being 750 watts of heat that's being transferred per meter squared of the tank. Now, that is a lot. Now, what we need to find is the total heat flow and not the heat flux. So in order to do that, you'd have to multiply the heat flux with the surface area of the tank. And we know that the surface area of a cylindrical tank would be pi times the diameter of the tank times the length of the tank. And since we have all of these numbers, if you multiply them together, you get a total heat loss of 5,253. So that's about 5 kilowatts of heat transfer from the tank. Now, that's a lot of heat that the tank is dissipating to the outside. Usually that is something that would be very costly, because if you want to maintain the temperature of the tank, you probably need to add heaters. Otherwise, the heat of the tank will dissipate very quickly, and that temperature will not stay at 50 degrees Celsius. And in order to do that, you would need at least a heater inside the tank that would counter the heat loss of the tank to the environment. Okay, so now that we have a high-level understanding of what convection is and how it operates, let's look at the final mode of heat transfer, which is the radiation that exists between surfaces. But before that, let's actually talk about the convection heat transfer coefficient a little bit more. And then when I talk about the boundary layer theory in another chapter, I'll dive into more detail about it.